Hi everyone, and welcome to this video on parallel plates. You obviously know what things that are parallel are and what plates are, and if you put two and two together, you can maybe sort of figure out what we're doing. But before we actually start talking about parallel plates, I want to talk about charges and the fields that they exert around them. So let's start there. So let's assume we have two charges. We have a positive charge and a negative charge. And we saw in chapter 7 some of this before. But we saw that there are fields that these create that are similar to magnetic fields. And so around a positive charge, we're going to have a whole bunch of fields that are being exerted away from that charge in this kind of direction. And the reason I know that they're being exerted away from the charge is we always do it when we have a positive test charge. We assume, okay, if I had a little positive charge in the presence of this big positive charge, what direction would it go? It would be repelled away. So that tells me the direction that electric field lines are going to go in this case. Likewise, if I have a positive test charge over here, those field lines are all going to go towards this. And depending on where I am, they're going to go in different directions around that. Now, if I had a positive test charge and I stuck it right here, what would happen is it would be experiencing a push in one direction from this positive charge. So it'd be feeling a push that way. And it would also be feeling a pull towards this negative charge. And so that's where we start to begin to see these curved lines, because the actual field line is going to look like this. And so if we were to start putting another positive test charge up here, we would see it looking like this, and we would see another one here looking something like this, another one here looking something like this, and then we get these field lines, just like we did magnetic field lines. We're getting electric field lines that look something like this. This, if I was to go back to this positive test charge, this positive test charge is going to experience a force right at that point in that direction. And then it's the vector sum of the forces from the charged objects that will influence the positive test charge. All right, and so when we're talking about the field that's acting on this, we have to think about the vector sum of all the fields from everything that's acting on it and combine those. And that's where calculus comes into play, which we're not going to get into in this course, but I'm going to allude to a little bit. Now consider these two positive charges here and here, and I'm bringing this little test charge, the positive test charge, into those presents. Well, what's going to happen is there's going to be a field from this one positive charge here that's going to be going in this direction, trying to exert away, and another one that's going to come away from it and also begin to bend, just like we saw with magnetic fields. And so if we were doing this, we'd see it bend this way. If we were coming from here, we'd see it bend this way. And so wherever we put the positive test charge, that's the direction that it would go. And so as I get further and further away, we're going to see this begin to happen. And so we know that around any positive charge, the electric field is directly towards it or directly away from it. So overall, what we're going to see is something that looks like, really like this, directly away from it, like that, in all directions away from it. And here, I'm going to see the same thing around this positive charge, because again, positive test charge is always what we bring in. One last thing I want to look at is an idea of bringing a positive charge into the presence of a negatively charged plate. We're talking about plates in terms of physics. We're not talking about plates you eat off of, obviously. We're talking about a charged flat object, generally a piece of metal that's going to be positively or negatively charged. Now, this positive test charge is going to be experiencing a field that is going to be pulling it towards that electron there in the middle. And it's going to feel another field that's going to be pulling it towards another electron, another field that's pulling it towards another electron. And so what we're going to get overall is we're going to get an unequal pulling of that positive charge. Obviously, we know it's going to be moving directly towards the plate, but it's going to get forces above and below it as well. So in this third case, because we have this extended shape, this long plate, what's going to happen is we're actually getting tons of directions it's pulling at, and we actually need to take the sum of all the vectors that are acting on that, all the different electrons that are pulling at it. Well, how do we actually do that? Because in theory, we have probably not an infinite number, but very close to an infinite number of electrons. And so at that point, what we'd have to do mathematically is we'd calculate the force of the test charge by dividing the charge on the extended object into a set of very, very small points. and we'd have to analyze every single interaction with every single electron. And what we would ultimately have to do is use calculus to find the sum of their influence. Now, we're not going to do that quite in this case. We're going to find some similarities and some ways to do this without having to derive the calculus, because that's beyond the scope of what we know at this point. But there will come a point, especially if you go on and do first-year physics or calculus first university, where you are going to be able to do that and derive that. So what's the electric field between two parallel plates? That is what I want to ask from this topic. So let's look at that. I have one parallel plate. There's one. It's positively charged. And I have a negative plate. Now these are always going to be oppositely charged. If they're the same charge, you're not going to get an electric field directly between them. And what we're going to do is, if I put a positive test charge, think about it, if I put a positive test charge right there, I would get a bit of a pull towards the electrons at the very end in that direction. I get a little pull there, I get a little pull there. So overall, we would probably be able to recognize that we would expect that this is going to be repelled from that plate and pulled towards the negative plate. Likewise, if I put another positive test charge right here, it's going to do the same thing. If I put a positive test charge here, same thing, it's going to be pulled in this direction between those plates. And when we start getting outside of the plates a little bit, it's going to be a little bit more curved, but nonetheless it will still pull towards the negative plate. And so what we see is, in between parallel plates, we get this electric field that always forms that is all in the same direction, and it's a pretty consistent electric field, provided we're not right at the edge of the boundaries of the plates. All the diagonal components, this one and this one, these are going to cancel out, and that's why this is going to be pulled directly across, because the one that's pulling it partially up is going to be canceled out by the electrons that are pulling it partially down at the same time. The electric field between the parallel plates is called a uniform electric field. It's called a uniform electric field. And so that's really helpful for us in physics, because if something's uniform, we can do a lot of things with that, and we can do a lot of experiments that are going to actually have some pretty interesting results, as we're going to see when we get to section 8.3. Obviously, if something's uniform, it means it's not changing, it's constant. The magnitude and direction of the force experienced by a positive test charge is the same for all positions between the plates. So the positive test charge here is going to experience the same force and direction as the one down here. So that's the nice thing about the parallel plates as well. There's almost no electric field outside the plates, and that is worth noting as well. So if we're out here, because in general these plates are very, very close together. Obviously, I haven't shown the very close together diagram, but if we actually made this, these are, because we're talking about just ions that are positively charged, they're very small molecules that we're looking at, or even elements or particles that we're looking at, and so those plates are going to be very closely together. So something that's out here is going to have a negligible pull on it. So there's almost no electric field outside the plates. And so we're going to say that's negligible. We're not going to worry about it beyond the plates. All right. So one of the things that scientists discovered as they went ahead and began exploring electric fields is the electric field is proportional to the charge. So whatever charge on the plates that I have, so we're going to make both plates the same charge, one positive, one negative, and divided by the area of the plates. Electric field is proportional to the charge on the plates divided by the area of the plates. We're going to assume that they're both the same area. So let's see an example of how this actually works. So let's consider the scenario where we have a positive test charge is placed between two parallel plates, and it's exactly in between these two plates, and we're asked what's the electric field going to be at 5 centimeters from the positive plate. Well, we already established that the electric field in between two parallel plates is the same all the way through. And so if I was asking this, you would say that the electric field would be 400 newtons per coulomb everywhere between the positive plates. And that's pretty intuitive based on where we've gone so far. Suppose I was able to ask a follow-up question to that, and that would be this. If I double the area, so what we're going to get is we're going to get twice the area that I started with of the plates, and I half the charge. So if I half the charge, I'm going to get 1/2 of the charge I started with. I think your textbook just keeps the charge the same. So what we can see is that a couple of things are happening here. If I compare EQ2, the second one, to the electric field that I initially had, what I can see here is that I'm going to have half the charge that I originally had divided by twice the area. That's the ratio compared to the ratio of Q to A, the original charge divided by the original area. And so what I can do is I can recognize that if I divide a fraction by a fraction, it's the same thing as multiplying. So the ratio of these becomes 1/2 Q divided by 2A times A over Q. And so really it's just a ratio question, right? So this is EQ2 over the EQ1. And so these are going to cancel out as well. And what you're going to be left with is half divided by 2. Well, 0.5 divided by 2 is 1/4. And so what we get by rearranging to get EQ on the other side, by multiplying both sides by EQ1, I get this. And so we can conclude that because it's 1/4 of the charge, or of the electric field that I originally had, it's going to be 1/4 of 400 newtons per coulomb, or just 100 newtons per coulomb. So if we half the charges on the plates, if we double the area of each of the plates, we would get, in fact, an electric field between those plates that's only 1/4 of what I originally had. The last thing I want to point out here is the fact that the distance between the plates has no bearing on the electric field. Distance between the plates does not affect the electric field. That's a surprise to some people. All right, one more thing just to discuss briefly here is the field and potential that is found on page 332 in your textbook. And you'll notice there that what they have is they have a diagram in that example where they have a negative charge up here and they have a positive charge down here. Now we know in this case positive test charge is going to go in this direction. We put that positive test charge in that. So in other words, we know the electric field is going to go in this direction, and the electric field is constant and the same at all points in between those parallel plates. Here's what is not constant. The electric potential changes. And so what they're doing in the example is they're saying, well, we're going to start at point A, which is 1 centimeter away, and we're going to use this equation that we have up above to figure out what this is. So we're going to say the electric potential at point A is the electric field times delta D. Well, what is delta D? Delta D in this case is the distance you are away from one of the plates. In fact, that distance that we're talking about of 1 centimeter is always going to be measured from the negative plate. Always measure delta D from the negative plate. And so what we get is that means that this delta D in terms of meters, we always want to put in SI units, is 4 centimeters or 0.04 meters. And then we do the same thing for VB. And if I put B here being 2 centimeters away from this plate, then we would be able to calculate that if we were given the electric field in between them. And then it's a matter of taking the delta V and saying it's the VA minus VB. And in the example in their textbook, they're able to subtract those and get 32 volts. The last thing they're able to do with that, once they have the electric field, which they were given in the question, is they just were able to calculate the fact that because the electric field is the force divided by the charge, we could figure out what the force is as well.